Well, I'm going to talk about this tree data structure today. I'm not sure why I'm doing this because it just come to my mind suddenly, like tree data structure. So, um, yeah. So here I am, trying to learn about how this thing works. So in fact, I've tried to go through this article already. So later I will not refer to the solution right there. I will try to implement myself and see if I can get what the algorithm is, like the data structure is, basic query and insertion algorithm. Well, the use case of tree is essentially like a prefix search where you can enter a certain text and then you find all the relevant text that contains the prefix. So it helps in optimization for example, like the auto completion and query suggestions, all this. Right, so to implement this is sort of like a graph structure where we have a root node and then it comes with different words. And when the words start with the same prefix, they will be falling under the same parent. For example, was and wax. They share the same branch, like the WA. So if it is a different one, then it will spawn another different branch, and then from that going onwards. So this structure helps us to do a quick search. For example, if I search for WO, I can then straight away go to W and O, and from here only I search for all the relevant tags afterwards. Like for example, they are under the leaf of this WO. For example, WORD, WORK, and WON. All these three. So there are three matches. If I search for WO. Well, here is another example where when the user search WA, then the algorithm will disregard, like don't need to search the entire thing in the right side already, because they will never match what user wants. So they go to the A and then go to S and X. So we can see that WAS, WAX are two words that matches the searching. Well, to do that, let me just go back here and to find out what is needed to implement a node like this, right? So first thing is definitely we need a tree node. So I'm using Python because it is very easy to write. So with this init method, we have put in a value and self.value equal to value. So I'm just saying that initializing a node, we will need the current value that I hold and also my children's value. So my children is going to be nothing and has ended equal to false. So has ended is a very important flag because it tells you that this sentence is full word. If not, then they will continue searching until it reaches the full word. Well, aside from that, do I need other things? Value children has ended. I think that would be it. The key thing is it's like a linked list or a graph where my current node has pointers to the direct children. So my W has A, H, and O as my children. Besides that, we have the tree data structure now. In the init statement, we can go through the self.root equal to tree node with nothing. So structurally, the first thing that I have right here is a tree node with nothing inside. So this is how we can get started, and potentially we might need other tools. So I will do it one by one. Right, now we have the root node. We also want a insert word like this. So whenever we insert a word, we want to make a tree data structure. So how can we do this? First thing first is we have the current node equal to root. So you can say current node is like a new variable that is pointing towards the position in the tree. So current node, firstly it will point to this root, the root node. And for every word in every character in the word, I want to make it check if the current node is part of the text or not. If not, then I will append it like a new node right below it. Else, I will then go to the next word and then set the current node into the next word. So if character in, okay, so this self.children, sorry, instead of a list, I can make it a map as well. So the structure will become a map, and then we have a child node with probably character child node or something like that. But we'll see how is it. I think like this is okay, because the structure is like when I want to do searching, I don't need to traverse through all the children. I can straight away point to that specific character and see if that exists. I think it's easier to do it in action, where for every character in the word, if the character in my children dot children, so remember the structure is, I put it on top here. Sample children, it can be like this. Oh, where we have a character, say for example W is equal to a node. So this node is a tree node lah. Like this. And we have other nodes as well right here in the bottom. So take this into account. If the character is in my current node's children, the reason why I don't need to check the current node is because we are starting with a root that is completely empty. So this empty node, it doesn't bring any meaning to our searching. So we can straight away search its direct children. So when the children exist, then I would say that current node equal to current node dot children character. So what this means is that it will go to the every single node that I have, and if the character, say for example I'm searching for WAS, inserting WAS, if W exists, then I would say go to here, go to the next node, because the current node, there are nodes that have already been created, and this node is okay. For example, if W already exists here, instead of pointing to the empty string, I will remove the pointer and point to the W, because everything at the other nodes, I don't care about it already. What I care is the ones that is matching my current insertion, right? So after we go to here, then I want to check again. I'll go to the next word, like next character, like A, and I'll check if A exists or not. If there is not exist yet, then I will append it right below the W, and my current node can be used because it is already pointing to W, and I can access to my direct children now to append the children into this node, right? So else, it's going to create a new tree. So new node equal to current tree node of a value, and this value is going to be the current character, and new node is going to append to the children current node new character dot children character equal to new node. So by doing this, I am creating a new node already to A. However, we cannot stop here yet because the current node is still pointing to W. If we stop here already, then the next word created will be attached to the W. But we don't want this. Now we want to remove the pointer to W and go to A. That is the reason why I'm putting in the current node equal to new node, right, to make it point to the latest node that I have created instead. Yeah, so you can see like current node is actually just a pointer. Go from this node and then go to next and then go to next whenever needed. Right, so we've created the nodes already. We can make a quick example on Trie, and then Trie t dot insert a node with say was, and t dot insert what and who, right? So it will become WAS right here. The intended behavior is WAS H A T, and the final one would be WHO. So there is no node at the right hand side, right? So now you can see the tree structure already. To verify that the tree structure is correct or not, we can do a quick breakfast search, I think, to see that the level, like different levels of nodes. This is the next level, and then this is the next level. To see that we have the correct structure right here. Well, we can do this by using another function called BFS. So BFS is going to be, wait a minute, do I want to, yep, actually I can. So I can do a BFS print to print the every single node to verify that I'm doing it correctly. So Q is equal to a self.root. Well, the first thing of BFS is also playing around with pointers. Now the first thing is in my queue, I'm pointing to the first current node, and there is something over here. I want to continue searching until my queue has finished. So I can say that if length of queue more than 0, I'll continue the loop. And the first thing is the first item is going to be my queue dot pop 0. So I pop the first node, like initially it has this empty node, and then I'll pop this and find all the children in it. Children is equal to first. So either I print it first, okay, like this, print first item dot value. Well, I can print it because it what I want is breakfast search. So whatever come into the queue earliest will get printed, which means that my queue will be W inside first, and then follow with AHOSAT. So it will become like the entire children of the second layer will get printed, and then after that's finished, the third layer children will get printed instead. So to continue with this, it's going to be very simple. We just add the queue first item dot children. So we add in all the children of the current node that I'm pointing. Like I've extracted the first item, get all the children, and I append it at the back. So that's how we can do the traversal. And I guess that's done. Let's see if this works. Alright, so t dot breakfast slash print. Let's go. Shit. Root is not defined. Line 35 17. Oh, it's a self dot root. 30 or 38. Oh, I cannot print like this. String of object has no attribute. So self dot root. Why is it a string object? Sorry. Honestly, it's not supposed to be a string because yeah, it's not supposed to be a string. As in, self dot node is Trie. Probably there's something wrong with insertion of the thing. So let's inspect a bit on what is happening. Created a tree. Insert the WAS, and then the next thing is when we want to do the printing. Every single node, if the character in my current nodes are children, and then I will say that current node is the next one, which I think is correct. And then we create a new node. Let's tell that the current nodes are children of car. Is equal to new node, current node equal to new node. I don't see anything wrong though. Let's see what's in the queue. Right? That's very, very strange. It's a tree node object. I'll pop the first item and I'll print the first item dot value and q. Oh, maybe I cannot do like plus equal, is it? For example, is I can do this excuse me. How about print is children? Oh, I know already. Sorry. It's going to be dot values. Okay. I print my current nodes dot value. Okay. Right. So just now I made a mistake. Excuse me. Right, the mistake was I assumed that the children is an array or a list instead of a map that is currently is. So when I try to plus equal, it sort of like making it become a toString or something and making the queue behaving incorrectly. So to fix that, I actually needed to add in the dot values because that will get all the values of this map and then make it become a list, so I can straight away concatenate to my original queue. Alright, so let's see if the printed value is correct. WAH yeah. So the layer like SA and AS is going to be flexibly interchangeable because map is essentially no priority one, so it can happen to be any number, any value. So another thing that I did incorrectly is this O is actually not the same label as the H. is the third layer level like this. So SAO is another layer, and then finally T. Alright, so finally we have done with insertion, and we are going to do the searching as well. Like so searching is going to be using a function called query self with a certain word, right? So when we are doing traversal, it's actually similar to the concept of insertion, but the condition is slightly different. So we have a current node pointing to the root node, and then for every character, if the character in my current children, I go to the next node. Else, instead of creating a new character, I will start do a probably I would say that it's let's break the loop. How about we break the loop and then we do a DFS search. Well, we have another issue on the insertion, because it doesn't tell us that the node here is ended. So we can say that it has ended now, ended equal to true, because there's a complete word. Is it no let's see. We have the character, and then we can say that the current node dot has ended. After the loop finish lah, we can say that it has ended equal to true. Alright, and then finally come back to the query. So query, instead of creating a new node, probably what I want to do is I want to do a searching from the point onwards, where oh, actually it is a must for the node to have, so I can return nothing, because it's a must for the prefix to exist. If it doesn't exist in my current node's children already, it does not make sense. I can straight away return the empty array already, indicating that none of the tree actually matches. None of the value in the tree actually matches the keyword that I'm searching for. Right. So I now traverse to the latest node of the character. I want to make it in a way that I can do a searching based on the pointer. For example, I search for WA. The current node has to be reaching A, and then after that we do a searching based on A as a root node. So we can do a DFS search on. I can do this DFS search based on and we can say probably result equal to empty string, empty array, and then the DFS search of the current node plus the result I put in here, and then we have the prefix. So prefix is going to be my word, but I don't want the last word, because the current node has the value of the last word already. Okay, so alright, I guess that wraps up the implementation for query. Actually no, after I get the DFS search, I want to return the result. Yep. Alright, in my DFS search, I can then say this is the node results and prefix. So from the current node equal to node for child in current node dot children DFS current node dot children child. This should be a character, and then DFS character with a prefix, with a result and with prefix. Okay, so here I get the current nodes already. If current node has ended, yeah, it's called has ended, I would then say that the current node result dot append current prefix plus current node dot value. Okay, get the value, and then finally for every single character go to the next level and get the result. The thing is based on the prefix plus probably current node or character is it. Okay, and then I will return the result. That's right. Oh, wait a minute. Oh shit, console.log. What the fucking hell. Okay, so whash, I got a whatho, and let's try with several use cases as well. This is an invalid case, this is a W case, and we also have a what case. Oh, so we put in the print. Right, wha error case, correct, and I can also add in another called whatever, see if that works. Yeah, so I got whatever already, and well, it looks like it works well. Because we haven't talked about how the query works, so I'm going to go up a bit and briefly explain what I did here. Right, so for the query, when I find a certain word, okay, query, it means that the first thing is based on the keyword like wh, we are going to make a current node point to the h. That's all. Yeah, so all this algorithm is based on the traverser, where I will traverse the character. If it doesn't exist already, I straight away return an empty array. But this is to save time lah, we don't need to do a DFS again already. And then we have a current node that will be pointing to the end of the node at the time, and then based on the current node I do a DFS search, and the result is where we catch the data and then we can return it afterwards. We also have the word this -1, that is because the prefix that we are looking for is, for example, wh. Then at the end of the for loop, our pointer will point to h, right? So h itself has a value of h, so the prefix should not include the h here, so it will be including everything at the left side, which in this case is going to be the prefix w. And this prefix w is then passed over to the DFS, where DFS also has the similar logic. We have a pointer to our current node that we are searching, which it will start with W. Sorry, it will start with H in this case. So it start with H, and then if the H already ended, has ended is like a stopping condition. When the stopping condition has arrived, I can straight away instead of returning a value, I don't return a value because there are situations like where like what and whatever T has ended, but it's not supposed to end the loop until end the depth search until it finishes all the possibilities below it. So remember to not return after, like, do not do like return a specific result here, because it will then cause the remaining like whatever to not be catch. Let me just show you like this. So whatever will not be included anymore, so we can just continue searching. Right, so for every character in the children, I do a depth search of the children and append. So result is a share, sort of like share result list. Any function can add into it, and then we add in the prefix of the original prefix plus our current node's value, because technically we are going one level further. So the current node, its value has to be remain. If we don't remain it, you will see that it's going to be, you're going to missing a lot of words, because you are not keeping anything that is in between, like here, like hash a is the in the, like, the middle, the nodes in the middle. If you don't put in the plus current value dot value, it will become WT only, ignoring whatever things in the middle. So that covers up the basic operations for Trie, and honestly it's a very fun data structure because it's a graph, and then sort of like a graph, and then to do a traversal you need to you can use either like breadth search or depth search, whatever things that you want to, and it will how to say, and just to achieve whatever things you want. For me it's a fun learning. Well, I hope it can help you in understanding the thinking process as well. I know there are a lot of existing tutorials out there already teaching data structures. So for me, I'm just sharing my thinking process when I try to recall how to implement the specific data structure. I'll try to implement or explore other structure as well, so that we can have more examples and more exposure on the how to think, for example, recursively, and how to think as a looping, and moving forward potentially find more difficult use cases and try to remember the pattern from there. Right, that's all for today's video. Thanks.